3D fluids and
ellipsoids.
ellipsoids. Okay,
Right.
I saw what it
Now,
says out there.
If
But
we have questions, can you repeat the questions? Because I'm hard of hearing.
okay, okay, very good.
Is the microphone.
I'll put that in my pocket.
And I'm assuming you're just using the chalkboard, right?
What?
You're just using the chalkboard, right?
Just chalkboard, yeah. And what do I do with this?
So you can put that anywhere on your shirt.
Okay.
About that's perfect.
Okay. So the title is 3D fluids and ellipsoids. 3D fluids and ellipsoids. Okay.
Check your microphone.
Oh,
Maybe slide it up.
all right, check it. Oh, testing 1, 2, 3? No?
Just take a look.
Oh, hi.
We're good. Just a little bit higher on the shirt.
Altieri.
Higher up.
No.
Finish higher up.
Like here.
What? Put it higher?
Yeah.
How's that? Does that work? Work? Okay. Okay. So volume preserving. 3D fluids, volume preserving, and ellipsoids. Okay, so so let's start with just a chart. Let's start with positive, definite inner products on V3, which is a real vector space. So I'm going to assume that, so this is the ellipsoid. If you look at the unit sphere, here's a picture of V, then you get some shape. That gives the unit sphere. Okay? So that's, and it's an ellipsoid. I kind of drew a round one, but anyway, I guess I could make it elliptical. Okay. So it has these three axes and these three chords, and it gives you the shape. And let's suppose the volume is 1, and I won't say that anymore. So the dimension of this space is 5. Because I have 3 numbers from those lengths, and their product has to be 1 or something. The product is limited. And then the position in space, so there are really 2 parameters from the shape. And then it has to be positioned in space. So that's another 3 parameters. 2 plus 3 is 5. Okay. Now, if you add a small symmetric inner product to a positive definite one, it's still positive definite if it's small enough, right? Because it's still symmetric and it's positive, so a small perturbation of a symmetric inner product will still be positive. So this has a natural, this 5-dimensional manifold has a natural tangent space, these symmetric matrices. And then the symmetric matrices are just elements of S2 of V, symmetric tensor product of V with itself. And this has a natural metric. If V has a metric, then S2 of V has an associated natural metric. So that means these tangent spaces for each inner product of that space. So here's a picture of my 5-dimensional space. It's 5-dimensional space. If you're at a point in this space, the tangent space at that point, as I've described it, has a natural metric. Namely, use this point to measure symmetric tensors. Symmetric matrices will have 3 eigenvalues, and you can measure them and stuff like that. So this innocuous sounding object here is quite interesting abstractly. It's 5-dimensional, non-compact manifold, and it has a natural metric. Okay, now I'm going to be studying fluids on, let's say, 3D fluids on triply periodic three space. Periodic three space. So this is the 3 torus. So let's imagine for each tangent space to the 3 torus as V, and then there's this 5-dimensional natural Riemannian manifold associated to that point. And we get an associated vibration. And then if you have a cross section of this vibration, this is a Riemannian metric on V. Wake up, Tony.
Yeah, well, I went to bed at 3:30. What time did you go?
Okay. So this is a picture of a Riemannian metric on V. And the volume form is fixed. So it's like I'm using the standard volume form on T3, and this is all the metrics on T3. And then if I have another one, I can measure the distance between these 2 points using that natural metric. And then I can take this and integrate that with respect to the volume form, the metric squared for each point, and take the square root. And that gives you a natural metric on the space of all metrics on T3. This works for any compact manifold. It actually works for any manifold formally, but the infinite dimensionality is easy to discuss in the compact case. Back to this thing, the linear automorphisms ought V acts on this 5-dimensional space because it acts transitively. It transforms one positive definite inner product to another. And the distance is measured by the structure of this symmetric perturbation, which eigenspaces and eigenvectors and so on. And they'll be transported by the metric because they're eigenvalues. Eigenvalues are conjugacy invariant. So ought V acts as isometries on this space. So over here, bundle maps would act as isometries on this space. Okay, so that's the geometry that I wanted to introduce. It's all based on ellipsoids. So that's the ellipsoids in the title. Now, a couple more points about this is this space, I won't give the proof, but this space has the following property. If you take any point, there is an isometry that fixes this point, and on the tangent directions, it's the antipodal map. For any point, you have this. So if you take any path, you can start and you cover it with little charts, little open sets where this picture, you can start reflecting about the point, and then the beginning point gets reflected about this point, and you get to this point, then you reflect again, you reflect again, reflect again, and you can compose these isometries and get a global isometry that takes any point to any other point. And this is the parallel translation of the metric also. So this is what's called a symmetric space, a globally symmetric space. So we have, Cartan studied these in They were, his studies of these and studies of Lie groups and Lie algebras were parallel. And this is a rank 2. The automorphism group, the linear group here is a higher ranked Lie group. So, and this space, one more thing, this space has curvature. Let's say if you normalize some discussion in the closed interval -1, 0. So it has negative and 0 curvature. And there are lots of interesting flat geodesic subspaces of dimension 2 inside this. These are flat and they're geodesic. Okay, and this is, so already we have something that, even though I spent 10 years following Thurston around with his discussions of hyperbolic geometry, this space to me is still mysterious because it has these 0 curvatures subspaces. So it's like this part of the space, I'm happy, comfortable. But the way these interact is complicated. So these ellipsoids are really will show how they're related to this. This is also a mysterious problem. And the mystery is, the germ of the mystery, I think, is here. When you discuss 2D fluids, this space becomes the hyperbolic plane. Exactly. And so we understand that better. And okay.
Why?
Oh, I'm taking too long.
What is the role of the ellipsoid?
What? No, you tell the question and he repeats it. So I make sure, and then you agree it's the right question.
What is the role of it being an
What?
What is the role of it being an
No,
ellipsoid?
tell him. Tell him.
What is the role of the ellipsoids?
What is what?
The role of the ellipsoid.
Wait. That's the answer. Wait. I mean, you have to wait.
Sorry. But I like your socks.
Okay, wait a minute. I'm off my track now. Wait a minute. So I'm trying, okay. Now I'm going to switch to fluids. So we'll circle back to ellipsoids at the very end. So you have to wait. Now I want to study incompressible fluid motion. So this is on periodic fluid motion on 3 space. And this equation was written down. You can read the years in my abstract for all the names. I'm not going to say any more about the dates and so on. But it's called the Euler partial differential equation. And I believe the first theorem about it was the following. So it's, imagine you have some volume preserving flow on this 3 manifold. And then you take a small, well, take any circle, smooth circle, say, which is homologous to 0, and then take the velocity vector field of the fluid and project it tangentially to the curve and integrate around the curve, that answer, and that's called the circulation. And as the fluid moves along, and this curve moves along, this is Lord Kelvin theorem about fluids, this circulation number stays constant. And that's a word sentence for what the Euler equation is. And that's the equivalent to the PDE. I won't write down any equations or PDEs, but that's a sentence for what it means, and it was first theorem. And then actually he used something 9 years before by Helmholtz. There's a particular generalized closed curve, which is Well, okay, now I'm going to answer your question because even though I said I wasn't. See, what happens when the fluid's going along? A piece of fluid moves along and it distorts into an ellipsoid. I mean, infinitesimally, like a round thing, a small piece. It becomes an ellipsoid of the same volume, and it rotates somehow. It has a position, right? So that I'm in that space. And this rotation is described, it has a direction, and it's a sort of an amount. And so you have all these directions, and they give a sort of generalized one-dimensional foliation, possibly with singularities, but I'm going to ignore that. And also there's a transversal measure that tells how much each one is rotating, how the elements are rotating. And this whole thing comes around and is like a generalized null homologous one cycle. So this was introduced like in the language of differential forms, which came later actually, but they knew about integrands and integration. And this is the Helmholtz vorticity. And it sort of resists bending because it's sort of the rotation this way is like a spinning bicycle wheel this way. And so it has angular momentum that resists. So this is moved along with the fluid, and this is invariant. And then Kelvin applied Stokes' theorem and just said, well, if I sort of compute the linking number of an arbitrary, in modern terms for this audience, if you just sort of compute the linking number, well, let me say it a little better. If V denotes the velocity, this is going to be denoted omega. So these are going to be almost the only symbols I hope to write down. There may be one or two more. I don't like symbols. Okay. I like words like wait or what. All right. Okay. Okay. So this is the velocity, V for velocity. I don't know why this would, well, it's a two form. So that's the natural notation for a two form. This Helmholtz vorticity behaves tensorially like a two form. And so he introduced this, and then Kelvin 9 years later came along and said, well, if you span this null homologous circle by the surface and you compute how many the lines go fluxing through, that's the integral of omega over this thing by Stokes' theorem. See, V corresponds via the metric to a one form. It's a vector field. And then with the metric, that's the same as a one form. Tangent space and cotangent space are the same. And then d eta is the definition of omega. And then the integral of d eta over the middle is the same as the integral of the restriction of eta on the boundary, but that's the projection of V onto the tangent vector. Okay, so we have the first word statement of Euler equation is the circulation moves with the fluid. The second equation is, the second word statement of this theorem, of the equation, is that omega is transported by the fluid motion. So omega at this time, fluid moves, pull it by the inverse motion forward, and that's the omega at the later time. So those are two-word equations for what's called the Euler fluid motion for ideal fluids. So you can see why a topologist trained person like me would have liked this equation and these descriptions of it, because it involves like chain maps. You know, we're doing algebraic topology here. Okay. All right, so Okay. Okay, so that's part one. Oh, sorry, I forgot about the line. Sorry. Uh, Okay, so I need to say any of that again? Okay, no? Okay. Okay, this is the second part. So now we're going to add friction. By the way, when Euler derived this PDE, he was just using Newton's law to write the equation. And you have a certain amount of momentum. Some faster stuff is coming into this slower stuff, so it pushes it, makes it move faster, and he just wrote that out carefully, and that Newton's laws gave the equation. And this is a word statement of what it means. Now, we can add friction because, if you're trying to run through water waist deep, it slows you down, right? Even if you're a tiny molecule, a molecular sized guy running through the water. Okay, so we add friction, which is sort of is observable as gravity in motion. Biologist Brown observed, you've heard all this, that pollen particles falling in the air in a room with the sunlight, you can see them, they'll go along jagged paths. They're being pulled down by the gravity. So that's the friction. So Brownian motion is a quantitative way to describe the friction. So if we add friction appropriately scaled to Euler's equation, we get the what's called the Navier-Stokes equation. Stokes has already appeared in using Stokes theorem. Calvin used Stokes theorem to go from Helmholtz to his statement, I think. Okay. Then these word sentences break down because of the friction. And the idea is that I'll keep drawing this picture of a simplified curve, but I'm going to apply it in a moment to the generalized. What happened to that? What happened to my vorticity? Oh, I didn't draw it. Oh, I didn't draw it. No, didn't I draw it somewhere? Huh?
Up above.
What? Oh.
At your eye level, when you pull it down.
Oh.
It's there.
Okay, well, just remember the vorticity is sort of, it's sort of like they go around like this. That's why it's a closed curve. But it's got this spinning thing to it. That's what Helmholtz. Oh, maybe it was, okay. So this, when you add friction, then what happens is the curves can move along and come close to themselves and then split and then touch and then reconnect. Or two curves could move along and come close to each other and combine. So it's a little like what we've heard about string theory. And these two operations can be formalized on families of curves. This is what one of the motivations to this string topology discussion, formalized in string topology. So these two pictures, and then at the dinner tonight, I will mention Fred, because these ideas and some of his great things we're connected at this point. So now let's go back to Euler again, back to Euler. I guess I could erase that. So we have two kinds of fluid flow, one where you ignore friction and one where you consider it. So Euler is without friction, the ideal stuff that has these nice word equations. Yeah. So let's see, this process here where you, you start from V and you use the metric to get eta, and then you apply exterior D to get eta, to apply exterior D to eta to get omega. I'll call this process D. Okay, that's the third symbol. Okay, I don't think there are going to be any more symbols. Yeah. Okay, and just some proper nouns. Okay. So a lot of simulation of these PDEs have been done, fluid simulation. It's a big industry. And the way you might do it is, for Euler, is like this. Let me just draw this down. So you start, you have the background metric on the torus. I'm going to fix the background metric. I've used it already here. I use the metric here. So this is the background metric on the torus. This will come in later. And you start from some time zero, some vorticity with the background metric, and then you do D inverse. We'll discuss what that means, but this operation, V is volume preserving, so div V is zero, and then there's a small normalization, and then this becomes a bijection with, and this is an exact form, exact two form. And this becomes a bijection between the appropriate for function spaces. And this is a little bit like part of the Hodge decomposition. Okay. This inverse, because you sort of take a short exact sequence and you split it using the metric. That's how you make the Hodge decomposition, right? So this is explicit, and this was crucial for later. But anyway, to get the velocity determined by omega, and then you use the velocity to start a motion, and then you transport to omega 1. I'm thinking of time isn't continuous, but it's in little bits like this, and I just do them bit by bit. Okay, so transport, so this, I'll call this T for transport. You transport omega naught to omega 1 by V. This is the velocity, so you change it slightly. Then you use D inverse again and find the velocity V1 at that time from omega 1, and then transport again to omega 2, and then apply D inverse again to get V3. Well, sorry, wait. V2, and then et cetera, like this. So this is an algorithm for solving the Euler equation. If you want to program it on a computer, you have to find this D inverse. That's the most expensive step on the computer. It's like converting a huge matrix. It's a linear operator. And this is an algorithm. And then this algorithm is useful you keep the algorithm, and this is the idea. You want to add the friction, which destroys the nice word sentences. But Brownian motion is like coin flipping. You sort of flip a coin, and then you go in a random direction, and then you flip a coin again, and you go in a random direction, flip a coin again, go in a random direction. And that probability process is in motion. And you can describe that by putting in little random translations at these points here. So you keep these the same, and you add to the algorithm a random translation by a small amount in any direction. And this will be an algorithm that will essentially add Brownian motion to that process. That's an idea, okay? So these are ways you could simulate the process. First, the Euler, which has these word equations, and then this is how you could simulate it. This is the expensive step, and then you could just put in a little bit of random translation, and that creates the Brownian motion. Okay. $240, okay. Something I can't read here. Okay. So the goal is to the goal is to try to obtain some a priori bounds given your initial conditions. Here you start with omega naught and you do V naught, and then V naught gets perturbed if you and then you get omega 1, and then omega 1 gets perturbed a little bit, and then you get V2 tilde, and then et cetera. Then you transport this to omega 2 tilde, randomly hit it with a random thing, and then do D inverse again to get V. This is V1. Oh, sorry. This is V naught, V1, V2. This random perturbation preserves exact forms, and then et cetera. Okay. So the goal is to try to get some bounds on this algorithmic process. And the idea is that to use the sort of kind of remarkable properties of this very mundane thing of the positive definite inner products on a three-dimensional vector space. It's this very interesting 5-manifold with all this geometry. And so you want to, you're sort of moving in this space, and I've been trying for a couple of years to stay in one of these flat subspaces, and I can 95% do it, but I can't do it I realize now. And so, and as soon as you start to sample the negative curvature, a bound which is tolerable, which is of order the size of what you have to the first power, is if you get into the negative curvature part, it becomes order of exponential of the size of what you have. So it's very hard to, in fact, even a 1.01 is disastrous here, because you know the differential equation x dot is x squared blows up. That's the standard one you do in ODEs. Any positive x log x is okay, but if you just pretend it's negative curvature, you have to deal with an exponential of the size you're at. So that's very bad. So you're sort of between the pillar and the post in this space. And you might say, well, wait, what happens in dimension 2 when it is totally hyperbolic? But there the tensors are involved are different, because a 2 form in dimension 2 is like a function times the area form. And a function, when you transport it, its values don't change. But here, the tensor you're transporting is a 2 form on a 3 manifold, which is like a vector field, because you could contract the vector field with the 3-dimensional volume, which is reserved, and you get a 2 form. And this is a bijection. So that's a natural transformation between vector fields and 2 forms in dimension 3, in dimension 3. And so you're dealing with the distortion of the tensor will involve the ellipsoids of the tensor you're transforming by, of the vector field you're transforming by. So then you have to study what happens. And you're sort of, at each point, you're moving around in this space, which has these 2 kinds of curvature, which either kill you or save you. Okay. So there's another, this is sort of, gave up on that idea. So there's another idea. Let's see, we'll do it here, I guess. So now let's erase this. This is like for the future. Let's go back to Euler. This is, if you get something for this, then you can try to attack this. Okay, so the idea now is that secretly Brownian motion is actually in this process as well. And that's because this process is, there's a metric step, and then you're basically looking at the inverse of d. So you're trying to solve the equation dx is given, where this is an exact 2 form. That was this step here. To find the velocity, or find the 1 form whose metric thing is the velocity, whose d is omega. So we're really computing d inverse. And so it's sort of an interesting coincidence. And you can read about this in Durham's book, where he discusses Durham's theorem, and lots of other places. But that's where I first read about it. There's some interesting analysis in geometry happening around what's called the Poincaré lemma, but we're talking about a global Poincaré lemma. But Poincaré lemma is where you solve locally. You find a primitive for a closed form locally. Okay, and so it's related, the actual formula depends on the metric, and it's related to Brownian motion. And so Brownian motion is sort of in this step, even for Euler. And, you know, Brownian motion is sort of scary too, because, you know, the paths are very jagged. they're sort of like they're like, because in a small time delta t, you move like the square root. That's the scale. So 1 over a million means you move 1,000, 1 over 1,000, right? Thousands, a million, right? Okay. So that's a lot bigger. So you have 6 zeros, you cut them in half, and you move that fast. But it's random, so it sort of cancels out, maybe. So anyway, it's almost 102 years ago, Wiener constructed a measure. And if you wanted to ask questions about these random paths, you would just put the question, this is a measure on the space of paths. So all finite paths, we don't know what they look like. I'm just drawing a picture, let's say starting from X to Y in the space T3. And there's a measure on this. And this is on the space of paths on paths. And then there's a projection map into T3 cross T3, which is just send the path to XY. And then you just take this Wiener measure and you push it forward. Push forward. And so you get a measure here, and it sort of looks like this. This is the diagonal, and the measure lives everywhere. As you move away from the diagonal, it goes to 0, and it has a pole as you come into the diagonal. It has an infinite structure as you come into the diagonal. So as you come into the diagonal, it's blowing up. So, and then this measure it's on the product, so it's sort of like a big matrix with a continuum number of entries, and you multiply, it's the linear, well, you do one other thing to it, which is another linear operator, which is more concrete, and you can see it, and then that's what D inverse is. This is sort of the main part of the matrix for D inverse. It's a kernel on the product. Okay, so then the question is, to derive the bounds that I want to derive, one needs to understand. So let's call this the mu. This is mu sub D inverse. It's the, well, let me just call it D inverse of XY. This is a function on the product. So it times the product measure is the kernel of an operator. So let me just call that D inverse of XY. That's what this measure is. So we sort of want, so what we need to know, one needs to understand this. I like to draw the picture. We need to understand this push forward of Brownian motion by how it depends on the metric. So partial of this whole thing with respect to the metric on T3. Because what happens, so I mean, there's a device here that the device I'm going to use is, as for every point, as a point moves through T3, the starting inner product at the point moves through T3, but it's sort of, it becomes a moving ellipsoid in the tangent space because you can transport the metric forward and you get a new metric and you have the background metric, so you can picture this as an ellipsoid. So this is associated, if you have any motion, you could do this, and any metric, you could just transport it forward and see how, measure the distortion. So we need to know And the transport, so, but what we're transporting is determined by initial data, which we understand completely by applying T inverse. And if we could control this in terms of the geometry, namely the metric on the space of metrics, then we could then transport it and understand it. And then we have to study D inverse again. But we only understand, what we understand is very well is how omega looks with respect to the transform metric. So this is another point. This is another point. If you have an object and you transport it to a new object and you understand it in terms of a metric, say G naught, this is W naught and this is W prime, then everything about this relationship will be changed. W prime in terms of this involves this transport. But if you transport the metric to a G prime, then the way these two relate is exactly the way these two relate. So the idea is to transport the metric along and then try to understand your algorithm in terms of the moving metric. So, and do induction sort of. So we need to understand how this Wiener measure changes. How does Brownian motion change with the fluid motion? And specifically, how does it depend on a changing metric created by the fluid motion? So now I said this was part of the Hodge decomposition, and the Hodge decomposition is, you have this map D to exact forms. Say this is, so this is onto, and there's a kernel. I don't have to write it. Subkernel. And then, so we have a kernel in here. So this is, you guys all know this, but I'm just learning it. Any map is a chain complex. Right? Haynes appreciate nodded. Because you can just, put 0 here and 0 here, and the composition is 0, right? So then you can treat it like a chain. Anyway, so I once saw Deline spending 10 minutes talk about this point. It was amazing. Okay. Anyway, but anyway, the way, in the Hodge decomposition, you split this chain complex, you might say. And then what does it mean? What does it mean to take an element here and find somebody that maps to it? Well, the kernel, let me do this better. So we're going to discuss, so now this is so Tony, wake up now, because this is when I'm going to answer your first question. How's the ellipsoid? No, you were asleep a minute ago.
No, it wasn't.
No, you were like this.
I was wondering when I was going.
You were like this, though.
No.
Is that how you pay
I
attention?
was going to ask you whether this.
I can't hear you. Sorry. Okay. Anyway.
I think I'm losing.
Okay. So this is really Mickey Mouse, but let me do it because it has some. So here's a vector space and a subspace, and here's the quotient space, and I want to. So I know how to invert 0. I'm going to just map it to the 0 of the subspace, but I want to choose a pre-image here. So this is in the coset of the subspace. So I don't know where to go here. How do I find something? If you have a metric, what do? See, here's the vector space. This is the one in the middle. This is the onto map, and I want to find this D inverse. So 0 here goes to 0, but some other point goes someone has to go to a coset of the kernel. Well, if you have a metric, you just, okay, sorry. So you have this, you have some point, let's see, you have this point in the coset, and so I'm getting confused now. So for each point here, I'm going to try to find the closest point. So I take the metric and go down like that. Sorry. This is not a very good way. So let's see. So here's the origin. I have all these subspaces transversal. And I have some point. I want to lift this. Let's see. So how do you find the perpendicular to a subspace? Oh, yeah, right. So then you find the closest point and then just translate this up to here in the coset. Is that right? Okay. So the idea is to, I claim the point to describe how the Hodge decomposition is changing. How to understand this is to understand how the closest point from a point not on the subspace to a subspace is found. So if you just have the round metric, then you just expand this out until you get to the tangent point. And then you keep doing this, and that'll find the perpendicular subspace passing through this point. And this will be the same all the way around. This will give you the, oh, I see. I have to think of a foliation to understand this. Right. Okay, right. Now I understand. You want to build this foliation. See, I don't think of subspaces. I think of coset spaces and foliations. Okay. So you find the perpendicular leaf. Here you have, given the subspace, you have the foliation this way, and you find the foliation this way by finding the closest point. Okay, that's this exact sequence got me off. Erase this. That's another point. Okay. Now, so this, so let's see. Let me draw a few of these. So if I have this point here, and if the metric is round, then I think of this as the center, and I have the metric, and then I spell out the unit sphere, the spheres, the constant distance spheres until they touch, and that's what tells me this point. So let me draw a nice circle here. Okay, so that's that one. Now, what happens, the same point, what happens if this is the point and the ellipse starts to turn like this? Well, I have to spell it out. I spell it out, and so the closest point moves like that, right? So this is something that, So now I'm back to ellipsoids again. I'm doing ellipses here, but ellipsoids, the same argument works when you have general ellipsoids in any dimension. So well, there's good news and bad news here. I think I'll just say that there's good news and bad news. The good news is if you just make a reasonable perturbation of this metric, so I don't know. Then if you just make a reasonable perturbation, this point seems to not move too fast, right? However, if you suppose you were very far away, suppose your ellipse looked like this, and, well, I mean, I'm going to draw the horizontal, the tangent like this. Suppose it's sort of, no, wait, okay, no, I'll do it differently. Let's see. If you have a long ellipse like that, and then, let's see. Okay, so now suppose the origin is here. I mean, the origin, the center of the ellipse, and then the closest point to the subspace would be like this. Now, suppose you just turn this ellipse slightly. Let's see. Then if you just turn it slightly, the tangent point moves very close to here. In other words, this slope is increasing very slowly. I haven't drawn it very well. So if you just turn it slightly, the tangent point moves very fast to here. That's the bad news. Now, okay, so hopefully you can carry out this program of estimates by only changing the metric slowly. And hopefully as the distance, as the path in the space of metrics gets longer and longer, this phenomenon is not forced on you. But this is work in progress. And I don't know. I'll stop here. We got back to ellipses.
Are there questions?
I could come closer, make sure.